who is going to be Mario Giuseppe Guaracciolo.
Guaracciolo,
sorry.
No, it's okay. Okay, can I start? Yes. Thank you very much. Thanks to the organizers to give me this opportunity to talk about EWOCS again. So let's start. EWOCS is our project which is focused on try to extend our knowledge about star formation and early stellar evolution on the superstar cluster. So just to give you a definition, when we talk about star cluster, we are talking about a cluster which is more massive than 10 to 4 solar masses, which is, of course, an arbitrary limit, but that actually corresponds to a cluster whose environment is dominated by a rich and variegated ensemble of massive stars. There are just a few clusters in this class that we know in the Milky Way. I plotted there on that map of the Milky Way all the clusters that we know, and you can see there are just a few, and also here in this mass distribution that I took from this paper, that this range in masses actually is very scarcely populated. But despite that, this type of clusters are very important because they really allow us to understand star formation, early stellar evolutions in starburst conditions, when galaxies form, where they experience a very intense epoch of star formation. The two clusters, we have started analyzing are Westerlund 1 and Westerlund 2, simply because they are the best targets to do this kind of science. Why? Because they are the closest clusters, superstar clusters to the Sun. They are very young. Westerlund 2 in particular is like 2 million years old. Very massive. Westerlund 1 is likely the most massive cluster we know in the Milky Way. They host compact objects, at least Westerlund 1. They host the richest population of massive stars that we know in classes in the Milky Way. So they really have all the ingredients that we need to do this kind of science. And what we want to do, as I said before, is to extend our knowledge of star formation, planet formation, early stellar evolution in this kind of environment. This means that we want to identify all the stars in these clusters, both in the core and in the extended halo. The extended halo is fundamental to understand how these clusters can form, how and if they can disperse. We want to select stars with disk and study the dispersal of protoplanetary disks in this kind of environment, and even talk about planet formation and evolution. We want to study the massive stars, try to understand how the high binarity in the massive stars that you can expect because of the very high density of the cluster actually affect the evolutionary pathway of the stars. We want to study the products of star formation, so IMF, brown dwarf formation, and all the other things that we can have in our mind. And also we want to study the compact objects that we can find in Westerlund 1. So a lot of science topics. These are just the most important that came in my mind, but there are a lot of things that we are doing. We are doing this science mainly with two data sets. Chandra observations, which are crucial to select the low mass stars in these clusters because they are brighter in X-rays than stars with a similar mass at the main sequence, for instance. So these observations allow us to pick up these stars and to study the high energy phenomena which occurs in these stars, in the massive stars, in the compact objects, diffuse emission, and also to perform timing and spectral analysis, because remember that in X-rays we tag each photon with time and energy. Then also JWST observations, which are crucial for selecting stars with disk, to select the very low mass stars, to study the properties of the cluster, and even study the nebulosities in this cluster. And as you can see, even unexpected things that pop up from always pop up from JWST observations. Together with new data sets that we have gathered and we are still continue to gather. So results. The first and only paper that we have published so far is the presentation of the X-ray catalog in Westerlund 1 from the EAS observations. We have identified and validated 5,400 sources in Westerlund 1. This is a very nice RGB image of the cluster. You can see the core of the cluster is very rich of point sources, but we also identified a lot of sources in the halo for the first time of this cluster. The brightest one is a pulsar. You can see, let me see. Here, okay. This is the pulsar. So we have a compact object, another one which is here that we found in our project. And we have selected almost all the massive stars, the most massive stars that have been listed by Clark and collaborator. And this really is the most heterogeneous sample of X-ray observed massive star in a young cluster. And the first sample of massive stars that we have analyzed are the Wolf-Rayet stars. Westerlund 1 contains the richest richest sample of Wolf-Rayet stars in Milky Way cluster, 24 Wolf-Rayet stars. 20 of them are observed in X-rays. The other 4 are carbon Wolf-Rayet stars, which are not typically very bright in X-rays. What we want to do is to analyze the high energy phenomena occurring in the stars, study the hot plasma in the stars, try to understand how binarity what role can play in the formation of such an ensemble of massive stars. And we are doing this thanks to time X-ray analysis. This is a time series in which you can see we retrieve a period that actually is confirmed by optical observation. This is the first time that actually we can retrieve an orbital period both in X-rays and radial velocity. And also spectral analysis, the spectrum of one of the stars. And in all these Wolf-Rayet stars, we observe this iron 25 line, which tell us that in all these systems we have plasma hotter than 10 million of degrees in colliding wind zones. So all these stars are in binary systems and are in binary systems with massive stars, which means that somehow binarity plays a role in the formation of such an ensemble of massive stars. Now let's skip this. Continue on Westerlund 1, diffuse emission. We are analyzing the diffuse emission in X-rays. You can see here the current map of the diffuse emission overlaid on the positions of the known massive stars. This is fundamental to understand how the hot plasma can accumulate in the core of the cluster and what role it can play for all the evolution of the cluster. This is the current status of spectral analysis of the diffuse emission, all the diffuse emission, the unresolved stars that we, of course, we have. We are analyzing this also because we want to find clues about the presence of non-thermal processes occurring in the center of the cluster, which are important for particular acceleration, for instance. So far, we didn't find any, but just because EAS is not the right instrument to do this kind of science. So we are trying to accumulate, to get new observations and to analyze the EAS, to continue to analyze the EAS data in order to try to find these clues about non-thermal emission. Now, how much time do I have left? 4 minutes, something like that? 3 minutes. Okay, 3 minutes to show you the JWST observations of Westerlund 1. This is NIRCam. It's a beautiful image that you can see in which the cluster really pop up with all these bright stars and some hint about nebulosity. Not only nice images, we also have wonderful photometric data in a set of wide and narrow filters. This is an example of a color magnitude diagram in which the red dots are NIRCam sources with an X-ray counterpart, which I said before, they are typically young stars of the cluster. And as you can see, in fact, they really trace here a locus which seems to be populated by the cluster stars. So we have a wonderful set of photometric data that will allow us to find the stars with disk, the low mass stars, and to study and quantify all the properties of the cluster, like the IMF, for instance. MIRI is the mosaic that we got for MIRI, where we found these huge and structured nebulosity that we are not expected actually to see. What I think that we are witnessing here is the interaction between the wind emitted by the massive stars during different stages of their evolution, but this is just an idea. We have to verify this. So the first thing that we want to do is try to understand what is all this nebulosity all around the cluster. But we want to use this data, of course, also to select the stars with disk, if any, to study their properties. And also, one thing that we were not expecting, to study the diffuse emission and the outflows that we observe around the very evolved massive stars. From the red supergiant, the yellow hypergiant, and some weird system that we have in this cluster, very evolved, we see these wonderful nebulosity, wonderful shells, tails, which are emitted by these, and lobes even, which are emitted by these massive stars, and that we want to study to understand what is the role of these outflows in the evolution of these systems, and what is the role of this outflow in shaping the environment in this cluster. So a lot of science that we are doing, and hopefully in the next EAS meeting we will have a lot of papers that we are going to present in our talks. Just to finish, also MERCAT radio emission in general can teach us a lot about all the interesting phenomena that occurs in the cluster. And in fact, as you can see, if you compare the MERCAT Galactic Plane Survey observation with the MIRI observation, you can see that all the blobs that pop up in the MERCAT observation actually lie on the nebulosities here, or the massive stars with shell. This is the 237, for instance, with a wonderful bow shock shell, and really pop up in the Mercat images. So there is a lot of physics that we need to study here by merging these data sets, and actually we are trying to even push the spatial resolution of Mercat, trying to get new data to push the spatial resolution down to 4 arcsecond, which would be great to trace the physics of the cloud, the nebulosity, and the shells around the massive stars. And I think that's it. These are my conclusions.